Microsoft recently announced a Majorana 1 chip. I actually saw it with my own eyes because I was at the conference in Santa Barbara. I think there is confusion in the community and in the public that some people think it's a working chip, and others are very upset that some people think it's a working chip. Okay, could you please completely clarify this situation?
What we showed Majorana 1 is a processor that includes the elements necessary to get to a scaled processor. Okay, or many of the elements necessary to get to a scaled processor. It's got 8 qubits. It's designed for single qubit to optimize for single qubit operations, but it also contains coherent links, which are necessary to connect one side of the qubit to the other. It has some simplifications that optimize for single qubit verification and are easier to manage electrostatically. But it has all the design elements necessary for large scale arrays because it's a small scale array, and this is what we're going to tile out. In addition, it has other important elements like the off-chip resonators. It actually has cryo-CMOS on it. So it is a prototype of what our large-scale processor is going to be, and it kind of demonstrates many of the important features. Now, in the interest of IP protection, what you see in the photographs is a demo setup that has all of the key components, the qubits, the readout, and control. Of course, what we carry around and what I showed at the meeting and what you see in photographs is not the thing that we actually put into fridges. However, we do in fridges have topological qubits. We have data on individual single qubit data on topological qubits. And we even have in fridges cryo-CMOS operating on topological qubits. So this is it's a demo it is a version that is IP that has some IP protections in that shows what is actually in many of our fridges today. And I think you may have seen at the meeting an SEM image of the chip. So you've seen what it looks like, and we are doing measurements on this type of processor. Again, optimizing for single qubit measurements and for testing out various of the components. But this is a real chip. This is not I understand this is not a rendering. Right, this is not just an artist's conception of what it would look like. There are actual chips like this. We have a roadmap. This is after the single qubit. This is the next thing on our roadmap. One of the next things on our roadmap. We have a bunch of or a number of tests that we want to do on 8 qubits that are on that roadmap, and we're marching through them.
Okay, very good. So the point is that this roadmap paper, which is posted on the archive, I saw it. So what you're saying is that that roadmap paper clearly states where you are going with this 8-qubit chip. And that is actually a scientific paper. This is not a news release. It's a scientific paper that is already on the physics archive. Correct? That's okay.
Correct.
Okay,
yeah.
Good.
So maybe thanks. That's a really good way of putting it. Which is in the roadmap paper we showed, hey, this is what we're doing, because I think maybe people need context. What is it, Mike? What is it that you're trying to do? We had in 2023 we had a paper on FISRA-B, right? In FISRA-B, which showed that which flexed the topological gap protocol and showed that we had these devices based on indium arsenide quantum wells and aluminum that we had made extremely clean so that we could pass this topological gap protocol. And that's strong statistical evidence that we have Majorana zero modes in those devices. Okay, and then the next thing is the Nature paper that came out a couple of weeks ago. We demonstrated that we could do parity readout. So we could tune into the topological phase or the regime around the topological phase, couple the wire to quantum dot, and now actually measure the fermion parity shared by the Majorana zero between the Majorana zero modes that you have in a topological superconductor, right? And so I don't know, it's not obvious that would have been the follow-up paper to our first paper, because another thing you could have done is you could have just worked on make the topological gap larger, just make the phase more stable, and just work on that and not do anything until you've gotten very large topological gaps and very large topological regions. Because the topological regions in that first paper, the gaps were 30, 40 microvolts typically, micro EV. We're not serializing in that way. We're parallelizing it. We're working on getting larger topological gaps. We're working on getting larger, more robust topological phases, and therefore better Majorana zero modes, more isolated further apart. We're doing all of that. There is actually, if you look at our data, incremental improvements in that, and especially in the yield. But in parallel, while we're making the topological phase better and therefore the future qubits better, we're also going to increase device complexity, because that's an additional piece of the puzzle that you can do more measurements beyond just transport measurements, right? That you can read out the parity shared by a pair of Majorana zero modes, and you can, and I'll come to this later, do non-commuting measurements, X and Z measurements, which is to say between overlapping pairs of Majorana zero modes. So we're moving along a complexity axis as well, or a functionality axis. That roadmap is explaining that. I mean, it does say, make some remarks about how the gaps need to increase, but the roadmap is pointing the direction of complexity. So now you understand, okay, you started with one wire where you're doing transport, topological gap protocol. Now you have a wire coupled to quantum dots, so you're doing readout of parity, which is the fundamental operation, in a topological quantum computer, as we've architected it. And then now we're going to two wires in parallel with 4 Majorana zero modes and measuring them in 2 different ways. That's the qubit work. And then there's an 8-qubit device, and that's what we've showcased.
Please elaborate on why you think, what evidence you have for existence of a single Majorana qubit from your perspective.
Yeah, great question. So without getting into too many of the technical details, looking at our roadmap or previous things that we've...
Just because I know the question that will come up, but you will give some of the details in your talk, right?
Of course. Yep. So I'll be talking through details in my talk.
Good, thank you.
So if you look at our roadmap, and many of the things we've written before, our plan is to make qubits that have 4 Majorana zero modes. Okay, so with a 4 Majorana zero mode qubit, if the total parity, electron parity is even, or fermion parity is even, you can have a qubit in which, like if I take 2 pairs, they can be even, or odd parity. Those would be basic states. So first thing is you have to have 4 Majorana zero modes. So we made it.
That's one qubit.
That's one qubit.
That's one qubit. That's what you call tetron, right? I just want to clarify the words also.
Excellent. Tetron is 4 Majorana zero modes, and that's 1 qubit. Exactly. And so first of all, you have to have 2 wires, 2 topological wires, which are connected in some way to be at the same potential, which we've done through a trivial superconducting bridge that connects them. So it's 2 parallel superconducting wires with a trivial bridge between them. It's an H structure. We wrote it. That's in our roadmap paper, but it's also in our 2017 scalable designs paper, right?
The sideways H. Yeah.
Sideways H. Okay. So first you have to make that, which we've done. Okay. And that actually involved a lot of important it turned out there were a lot of important fabrication design advances going into that, because the data coming out of that is very high quality. So that's really exciting. Both of them have to be in the tunable into the topological phase, because as I said, the yield is not perfect on wires. And so you need to have both of them in the topological phase. That turns out to be, because of the improvements we made to design and fabrication and materials, we have that as well. And then crucially, they have to be in the topological phase at the same value of the magnetic field, because we can tune the density differently on the 2 wires, but it's one global magnetic field. So it's not enough that they both have a topological phase. They both have to have a topological phase at the same field. Okay, so we have devices that do that. They both have both wires at topological phase. They both have it at the same field. So that means that at the same...
Hold on. How do you ascertain that you have devices like that? You are doing your phys-rep-B experiments separately.
Exactly.
Both wires.
We run the topological gap protocol on both of those wires, and they pass. They have topological regions identified in the protocol, and they overlap in field. So that's number 1. Number 2, then you have to be able to do these fermion parity measurements, because that's the fundamental operation. If you do that on one wire, that's essentially redoing the Nature paper, okay? But doing the Nature paper in a qubit configuration, okay, where you have actually 4, even though I'm only measuring 2, I have 4 of them. So it's in a qubit configuration, and it's measuring the parity on one of the wires. So that's like a measurement. If you think about conventional qubits, that's a Z measurement, right? You're measuring in the Z basis. You're doing a projective measurement, a non-demolition measurement into Z equals +1 or Z equals -1. Good. But then the additional thing we've done is we've done what you would call an X measurement, is you measured a similar kind of quantum capacitance measurement on a quantum dot on two Majorana zero modes that are on two different wires.
Yep.
So this involves an interference loop that connects Majorana zero modes on two different wires and goes through a trivial, fully gapped aluminum backbone as part of the loop.
Yep.
Which,
So this, you connect the two ends of the wire, correct?
Midpoints. So actually, the So the midpoints are connected with the trivial
Right.
aluminum, and the quantum dot connects the two ends. Correct. So there's a loop now, okay, where we're measuring the fermion parity along that loop, which actually bridges two separate wires. It doesn't commute with the first measurement because it's touching, was one Majorana zero mode in common that's being touched, and we've done that measurement as well. Now, what's interesting is we actually see two timescales now, okay? Because they're different kinds of error processes. It turns out we have a very biased error model in this device, okay? Which I guess in retrospect, you could have guessed this is true, but we actually have done the measurement and we see two very different timescales. One timescale, which we see in the Z measurements, which we also talked about in the Nature paper, is, it's longer than a millisecond. So it's a pretty long timescale. It doesn't seem to have much to do with temperature. Okay, it looks like it's primarily a function of the shielding and filtering, and it's totally consistent with just quasi-particle poisoning. You have some excited quasi-particle, probably far out of equilibrium. The density of them appears to be less than 1 per micron cubed. One of those excited above gap quasi-particles comes in and gets absorbed by a Majorana zero mode.
It's basically a stray electron somehow moving around in the gap. It's just a stray electron, maybe cosmic ray, who knows?
Yeah.
It's a stray electron.
We think it's probably actually caused by it's infrared radiation, probably 4K radiation. Okay, some of that can leak in. Our box is as light tight as possible, but there is some black body radiation from the 4K stage. That's much larger than any of the gaps in the system, and it will create excited quasi-particles. That's what we suspect it is. And as we've made some improvements in shielding and filtering, it looks like that causes some improvement. Okay, but those are there. It's a pretty slow process, and we see these switches on this time scale that's longer than a millisecond. That's kind of the dominant thing in the Z process. What dominates the X process, that's a dominant in the Z measurement. So those are effectively some kind of leakage error. Now, the thing that was dominating in the X measurements is we actually see tunneling between Majorana zero modes, it looks like. And those tunneling processes between Majorana zero modes occur on a time scale that's around 5 microseconds. That's controlled, the process occurs within a single wire, controlled by the topological gap, which is around 30 micro EV. So that's a scale, which obviously is a much shorter scale, but it's also a scale that we can improve by making better topological gaps. If you make the gap larger, then this process, and that is in essence, the promise of topological protection is if you can make this one parameter larger, the gap, right, and the coherence length, which is closely related to it. If you can make the gap and gap larger, coherence length shorter, or topological coherence length shorter, then you have a path to make this time scale longer to make the qubit better and better, right? Without making painful sacrifices, meaning that the qubit doesn't become larger, it doesn't become slower, because it's the same energy scale and length scale that controls those. So, there's a path to make, and it also, by the way, there's a second path, which is make the qubits longer, a little bit longer, and that also, if you're in the exponential scaling regime, tunneling from one end of the wire to the other.
Well longer, okay.
Yeah, make the wire longer. So what's really exciting is we see these two error processes. They appear to be, there's a simple explanation for why it's two very different timescales associated with them, and they're coming out of doing two different, non-commuting measurements. So that's the basic functionality of a qubit. Another way of saying it is, it looks like a two-level system, very clearly. We have clear evidence for a two-level system, and we can do measurements. And what's one of the cool things about it is the way we do the X measurement is not by doing a Hadamard gate and then doing a Z measurement. It's just by directly doing the X measurement. So
let me then probe, just for my understanding and maybe for understanding of the community, what you just described. I know you will describe it in details in your talk, but it's a 30-minute talk. We actually have a bit more luxury here. So I think that the Z measurement is conceptually simple. the Z measurement, because the Z measurement is kind of independent of all this Marana and so on and so forth. Okay, of course your system does those things, but it is independent. Okay, meaning it's directly seeing how good your gap is, and the gap is very good because you are getting milliseconds poisoning time, and you can. Important thing is that in your actual device structure you can do this Z measurement. Okay, that's you have demonstrated that. Okay, are you saying that the X measurement is essentially seeing a Marana splitting in some form between two non-equivalent Maranas because they are in different wires, they're not in the same wire? Is that what you are seeing? Because you have brought them close together and there is a little splitting. That of course is part of your two-level system. So again, I know I'm simplifying it, but trust me, it's very important.
No, that's a great point. So we have 4 Majorana zero modes. We by coupling 2 of them on different wires through a quantum dot, we have effectively put a splitting through the dot on those 2 in order to measure them, right? We put a splitting between the 2 parity states of this pair in order to do the measurement. But we're sensitive to the splitting on a wire, the splitting between these 2, right?
It knows that other Marana is there. Exactly.
It knows the other Majorana is here, and it knows that splitting. In the measurement configuration, we don't see a coherent rotation associated with that because the measurement is, because we're looking at this, we're measuring this, but we are sensitive to effectively, flips, relaxation processes associated with tunneling from here to here, and this other measurement, and knowing about this other Majorana zero mode over here.
Yeah, so the splitting then, in the end, your measurement has a time scale, which you don't have to tell me now. These are things you'll talk about.
Yeah.
In the end, the X measurement, Z measurement has above millisecond time scale, and that's kind of poison. Okay. X measurement also has some time scale. Okay. And what I'm asking is that, maybe you just answered, but I just want to make sure that I understand. Is that time scale connected with Marana splitting in the same way? Is it the intrinsic Marana?
It's connected. It also depends on other things like noise and so on, but it is connected to it. Correct.
Suppose it was ideal situation. Suppose you had no decoherence of the Marana. I mean, it's always good. Your theory is always good to think about the ideal situation. So if your ideal X-gate measurement, the one you're calling X-gate measurement, is really looking at how much Marana overlap, to what extent this thing are Maranas. So it's looking at the splitting. Okay, then there are of course other things coming in. Is that correct? Is that a correct statement?
Yeah, I would say the limitations on this. So the limitations on this X measurement comes primarily from Majorana zero mode overlap within one wire.
Good. Okay, then that's where.
So another way of saying it is, if we by making the wire very long and the gap very large, or the coherence length very short, so you have e to the minus the length of the wire divided by coherence length. If that's very small, then the flips that we see during an X measurement will become more and more infrequent. That time scale will get longer and longer, and that is, I think this is what you're saying basically, is like that is the reason for wanting to make topological qubits, right? Because there's a very clear path now, because it concentrates your effort on one very important problem, which is make the improvements you need to make this gap larger, and then if you do, lots of things will simultaneously get better.
Okay. No, I thought that was the answer, but I wanted to make sure. And that's what I meant by the ideal system. The system was ideal. This time scale associated with the X measurement would also be very long, because your Majorana in a single wire are then in what you and I call exponentially protected regime, which is not something that a regular journalist will use. But you and I both know that what topology is just a synonym for exponential protection. Okay. In fact, I would add a little bit to this, since I do know that even the short time scale is very long compared with microscopic time scales. This I know, because if you have microscopic time scales coming from a random noise, that's like a few picosecond. And again,
so it's much longer than that.
Of course, I'm not involved in the experiment. I did not make it very clear. I'm not a Microsoft employee, and I was never a Microsoft employee. And I'm a very technical person, as everybody knows. So this I understand. This is what I thought what it is. And this is something, it seems to me, you will have to continue improving if you are going to get to a topological quantum computer. Am I correct? This time scale for X-gate has to be longer than what you have now, which is the first measurement.
Yeah.
And I will add something to that again for the community. that I'm old enough to remember when Transmon, which are the leading qubits now, first experiment came. First experiment was Nakamura's experiment on Cooper pair box. The time scale, this coherence time, in that case T1, was a nanosecond. That time scale now is 100 microsecond. It took 20 years to do that. So these time scales improve with improvement in technology and improvement. And what people often forget, that in the qubit that you are trying to make, which, as you know, original theories we did, as this is not bragging, this is just a fact, is the physics is just 10, 12 years old. We just allow, and the other ion trap and Transmon, the physics was already completely known 50 years. So as you're creating a technology, you have to figure out the physics also, which makes it very, very difficult.
Right. That's right. Now, everything you said is correct.
Mm-hmm.
Now, the reason that I'm very optimistic that this is not now a 20-year journey, this is not the starting point of 1999 or something like that.
I was going to ask you, how did I start with 50 more years? Yeah, please tell me.
Yeah. So the reason is, well, look, because we have worked out what our roadmap needs to be, what the milestones we need to accomplish along the way. So we've done, that is the DARPA, US 2QC program that we're in, was, to enter into this contract with the US government, we had to actually provide a roadmap. Like, what are we going to do? What are the technical accomplishments we need? When do they need to happen? How are they impacted by what's our hiring ramp? What are our budgets? What are the supply chain issues? All of the practical matters that go into going along a roadmap. We had to work, worked out all those things. What is the architecture? What is the architecture at scale that we're going for? And given that, what are all the things we need to develop along the way, and when do we need to develop them? So in essence, you could ask, like, how long will it take you? And the answer is, well, we've worked out all the steps along the way in varying degrees of detail. So to the fault tolerant prototype, we worked out in a lot of detail. From there up until utility scale, not as much detail, but still considerable detail. So we have a lot of understanding of what the dependencies are of the different work streams, what the work streams are. We have a lot better understanding of what our cycle time is from chip to chip and device family to device family. So in that sense, it's not just, I'm not just guessing. I mean, we actually have a roadmap that has timelines associated with it. And so based on that, look, obviously there are unknown unknowns can always come up, right? That's just the reality. And surprising things can happen. But having said that, we have a pretty good idea of the things we need to do to increase the topological gap, make the topological phase better. And we also have a very good idea of the things we need to do to make the devices more complex, to have more qubits, different control systems, all of the components that have to come together to make something complicated. I mean, look, a topological quantum computer, or any quantum computer, is going to be an extremely complicated thing. But, like rocket ships that go to outer space and launch satellites are also extremely actually, your car is extremely complicated, right? And there are many different systems that have to come together. So in that sense, yes, or a data center is an extremely complicated thing. People build extremely complicated things, and there is a process in place for doing this kind of thing. And we have leaned on those kinds of planning processes.
This I completely agree with, because the difference is that the basic physics here is known, and as in my talks, I give a guarantee that if somebody makes the system we have in our paper, indium arsenide nanowire, spin orbit coupling, proximity superconductivity, a magnetic field tuned in the right regime, you are guaranteed to see Majorana. I guarantee it. If you don't see it, because this is mean field band structure theory, it never fails. If you don't see it, there is some extraneous reason that you did not think about. Maybe it's disorder, maybe it's something else. And that's something that can be solved in a technological way. It cannot be solved in university laboratories, I can tell you that, okay? It requires a technological mind to do it. And that's what you're doing. You have so many people working on it, and you do all kinds of risk management. You know what could go wrong, and that's what you're saying. In university context, it's impossible to do that. I was talking about university will take 20 years, 30 years. What you are saying that no, in your case, you know what the possible problems are. You're continuously making sure that they are not your roadblocks. I mean, I totally understand. And I do not think this problem, this project can be taken in any university under regular kind of NSF type support, because this is just a technological project. The problems are huge. Okay. Topological gap to me is the physics. As you and I know, in our favorite fractional quantum, all favorite fractional quantum hall is exactly the same thing. Gap is the protection. Okay. We talk about the word minus L over C, but C depends entirely on inversely on the gap. So topological projection is potential minus gap. You make the gap large. What I'm saying, as you and I know, gap is the most important thing. And the gap has large, gap has dimension. What do I mean by large? You and I know. But I would contend, I'm expressing my opinion, Shankar Sharma, the physicist, that 20 microvolt is too small a gap to create a quantum computer. I do not know what the number is. I personally be happy. I personally be really satisfied with 200, but I'm not trying to create the technology. There's always a compromise. So you don't have to give me a number.
Just over the course of the last year, I'd say our average is a little bit higher, probably tending closer to 40, on average. Now, for the 8-qubit processor, our target there is our target. I don't, we look, there's a little bit of estimation, so it might work pretty well even with lower gaps, but our target is around 70 microvolts ultimately. Okay, that's what we wrote in the roadmap paper. And then for sort of the multi-logical qubit kind of fault-tolerant prototype stage, it's it's around 100 microvolts. So that's and actually after that, the improvements don't have to be that big, because the nice thing is, as you know, these are sitting in exponentials. So when you have something sitting in exponential, we are not, just to be clear, there are lots of things that you want to improve. We're not trying to improve by an order of magnitude. We're not trying to improve by, we're really, in a world where a factor of 2 or 3 improvement in the gap is enormous. Okay. Yes. So that's one of the really important things to say about topological protection is it's actually, in the grand scheme of things, fairly modest improvements, modest changes in how good your qubit is. Right. And, it's not a great mystery what the basic limitations are. One is disorder. Okay. Disorder is something that we've actually got the disorder to be really low. I mean, if you think about the localization lengths that we have in our devices, localization length is 2 microns, or certainly over 1 micron, in some cases as long as 2 microns. So these are very...
How do you know that? I'm going to give an opportunity to explain how do you know.
So we know that because we make these devices, these nanowire devices of different lengths. We measure the non-local conductance across them and then put them to an exponential scaling as a function of length, and they fit pretty well to exponential scaling. And we know what the density is in these devices because we go to the depletion point and we actually see subband transitions. So we know in the lowest subband we can get localization lengths longer than a micron. Okay.
So you are doing piece by piece ballistic measurement, right? Of and you can put it together, and you are getting roughly 2 microns. So
it's not ballistic, because there is we are observing the localization length. So we're seeing, there is a localization length, the localized states, and we're seeing, when you say that you're fitting into an exponential, it means you're seeing the tail of the exponential, right? And we see, and just to be clear, we see significant transport even across 4 micron long wires. Okay, so in the lowest subband. So now that's an integrated thing, right? That's sort of telling you about the overall quality. But if I take apart in pieces, the disorder, there's disorder in the quantum well, and there's disorder due to the dielectric. And if you look at the mobility of just our quantum wells near surface, we have mobility over 100,000, right? So these are very, very clean in that sense.
Your quoted number is 60,000, not over 100,000.
Yeah, that was in 2023. A lot has changed since then.
These are very important points. These are very, very important.
So
you have 100,000.
I'll talk about this. I'll mention this in my talk on today. So we have seen continuously made improvements to the mobility. Second thing is the wire quality. You're putting down some aluminum. You look at the quality of the wire. You'll see just the roughness and smoothness of the wire. I'll show images in my talk. You'll see how smooth these wires are. So you can see the improvements to the wire quality and how good the quality of the wires is. And if you look at cross sections, you'll see the quality of the interface is very high. So these are things that we're continuously improving on, but these are very, very clean devices. We will make continuous improvements. Okay, that I can guarantee you. We're making continuous improvements. So disorder is something that I think you will see continuous improvements. Those continuous improvements will be reflected in the spread in gaps that we observe, and it will be definitely reflected in the coherence length, the topological coherence length, in the disordered coherence length. Now, so that's number 1. Disorder, we're definitely continuously improving that. Number 2 is the spin orbit coupling. Okay, spin orbit coupling is also a limit on this, and so the spin orbit coupling, that is something that we have a bunch of ideas that we've proven out sort of in quantum wells and made progress on. on how to improve spin-orbit coupling. We actually already have improved spin-orbit coupling. The work in the Nature paper and our qubit is in a stack with larger spin-orbit coupling that we had in 2023. So we made some incremental improvements to spin-orbit coupling. That is part of why we have larger gaps and higher yields. We're continuing to work on that. We're going to increase the spin-orbit coupling, continue to increase spin-orbit coupling. And the third thing is the superconducting gap. Okay, and the superconducting gap we made some modest improvements to just by changing the thickness of aluminum. You know, the aluminum is thinner. Aluminum has a higher gap than thick aluminum. That's one of the unique properties that aluminum has that other materials don't have. So that's one of the nice things about aluminum is that by having better control over aluminum, making it a bit thinner, we've got a little bit larger aluminum gaps, and that again, small improvements to things that are going to sit in an exponential lead to big improvements. So those are the things we've done, but you know there are other ways to improve the gap, and we're going to continue. We're going to continually reduce disorder. We're going to continually make the spin-orbit coupling better. We're going to continually, or in some cases maybe step functions, make some improvements to the gap. These are all things I'm really excited about, and stay tuned. But as I said, we chose very intentionally not to serialize the work, not to first get the largest gap possible and then try to make qubits and multi-qubit devices. No, we're doing these things in parallel.
And you made a number of significant comments. By the way, again, for those who are would be listening to this, the gap is proportional to the spin-orbit coupling. So you increase spin-orbit coupling, gap increases. It's as simple as that. And there are a variety of ways of increasing spin-orbit coupling, but it depends on the asymmetry in the system, and that can be controlled by external voltage. I mean, that's what you're alluding to. I'm just clarifying. Okay, I mean, I have said many times, as you know, we had a very well-known paper saying that these are absolute necessary conditions before we can talk about Majorana. What are sufficient conditions? Sufficient conditions, unfortunately, is what we call braiding. There is no other sufficient condition. I'm sorry. Okay, when you have necessary conditions, you should immediately go to braiding, which you do through measurement. Can you elaborate on it?
Yeah, the topological gap protocol. It's important to point out that there's a way in which it's a statistical criterion, and the reason is because, as you said, you need to have zero bias peaks at both ends of the wire. One end's not enough; it has to be both ends of the wire, and they have to be stable. Meaning, if I change something about the junctions, then if it goes away, then that tells you that that probably was just some local bound state. And since we're talking about a phase of matter, topological phase, if I move through the bulk phase diagram, like if I change the magnetic field or if I change the density, they shouldn't go away immediately, right? It shouldn't just be one point in the bulk phase space. So it needs stability. Now, on the other hand, how stable is stable enough, right? Because we know that sometimes, and you've written extensively about quasi-Majorana, quote-unquote quasi-Majorana zero modes, that there can be, due to the shape of the potentials at the end of the wire, there can be accidental or semi-accidental, low energy Andreev bound states that actually are pretty stable. Like probably when you first did the calculation, you were surprised at how stable they were, right? They can be more stable than people would have expected. So then there's a question, which is, how stable is stable enough, right? And similarly, we say, well, a phase transition is caused by a gap closing and reopening, right? Well, in a disordered system, you get localized states that come in and just close gaps for no obvious reason, right? No deep reason. There's localization. There happen to be some localized states that are low in energy because of the local potential accidentally. So you can get gap closings at some point in the phase diagram just accidentally, right? So both of the things that we're talking about, which is zero bias peaks and gap closings, can happen for reasons that have nothing to do with or relatively little to do with Majorana zero mode physics, right? So you have to have some understanding of, well, how stable is stable enough, and how extensive a gap closing and reopening, how robust with respect to parameters, because there can be an accidental level crossing, for instance, at one point in phase space, but how robust with respect to varying parameters should that gap closing be? And the answer depends on the disorder level, right? It's going to be very different. In very dirty devices, it will be easy to tell whether you have a topological phase or not, because extremely dirty devices, you almost never have a topological phase. So anything you can see, you could almost say, this is just some trivial thing. And in very clean devices, the signatures are very clean, and the topological phase is very large. And so, in very clean devices, it's easy. It's in the intermediate where it's not perfectly clean and not very dirty that it's tricky, right? And it depends a little bit on the level of disorder. And so the topological map protocol has a number of parameters in it because you take an extensive amount of data, over bias voltage and field and density, which is controlled with plunger voltage, and you vary both of the junction transparencies. So by varying many parameters, we make sure that the zero bias peaks are very stable, like relative to kind of the sort of baseline level of stability that you can accidentally get, that the gap closing is really robust and extends over a region in phase space, and that it's actually a gap closing that is the boundary of a region in phase space, and that all these things are happening together. And those are some thresholds that you put in that are basically statistical. Now, the reality is that people maybe don't fully appreciate is we cannot guarantee 100% that when you pass the protocol that it's topological. Some things that fail the protocol actually are topological because, again, the protocol is taking some very vast continuous data, which is not topological, and it's giving you a binary answer, topological, non-topological. Now, there will always be some edge cases that are sort of borderline pass or borderline fail. If you change the protocol a little bit, some of the borderline passes become borderline fails and vice versa. That's the nature of a protocol like this. That's a statistical criterion. If you change the protocol, you'll get a little bit different answers. If you change the data a little bit, you'll get a little bit different answers. So small changes lead to small changes in answer. But the edge cases, it turns out, is not most of the cases. Most of the cases are clearly one or the other. And so the protocol turns out to be pretty accurate and is pretty convenient. And when I say pretty accurate, it's really better than, for what we believe the disorder levels are in our devices.
So if you see multiple devices, very similar physics using protocol or whatever, then the fine tuning, you are lowering the probability of fine tuning, right? This is how statistic goes. So I assume you have seen it multiple samples, very similar physics, right? Yeah. Very similar effects. I don't even want to call it physics. Is that correct?
Yeah. So if we just talk about the topological gap protocol, we've run the topological gap protocol. We've probably tested, over 100 wires, and we've seen our yield increase over time, over that time period. So this is not just one or two things where you see a little blip on something. We're getting to the point where you could say we actually have real statistics, right, on passing the topological gap protocol, and for different sort of generations of material stacks as the materials have improved. So there, I think we have a lot of data for the parity measurement. There are two devices in the Nature paper, and actually one of them, there's two measurements on that device separated by roughly a month. So and during that month, various voltages were cycled. So a lot of settings were quite different in those two measurements on device A, and then device B is an entirely different device. Over the year since then, that's become a moderately routine measurement. I don't know the exact statistics, but we've done that measurement. We've done plenty of times. On the old, and in fact, you're seeing that again on the new device. Is one of the measurements on the new device design, and we've measured a bunch of the new devices as well. So we're certainly with qubits. We're not at the point yet where I can quote you like statistics and say statistically meaningful things, but I can also say with a lot of confidence that we will. Like over time, we're going to accumulate statistics, and actually, in many ways, that's one of the nice things about the multi-qubit chips is because we built this. Because we've put a number together on a single chip, we can now start to accumulate statistics a lot faster.
Let me just take a quick look because I think we have covered everything.
Awesome. Awesome. Hey, I got to jump to the next thing. I'm sure you're busy too. Thanks. Have a great weekend. I'll see you in Anaheim.